Okay. Okay. So coming back to the comparison with experiments, we had kind of seen this table at the end of the previous class, and we see that the mean field values are different from what you see experimentally. The experimental values seem to agree with the simulations done on 3D Ising model quite well. So the last column is the computer simulation. The 2D Ising model are the exact values because it's an integrable system. You can well, not just integrable.
Sir.
Yeah. Yes.
Sorry to disturb you, sir.
Yeah.
I didn't hear the class.
Oh yeah. There was a class on Monday. I was supposed to send a mail. In fact, I forgot actually.
Actually, so, what are the timetables, sir? I think we have class Monday 9:30 to 11 and Friday 9:30 to 11, and this day.
No. You are talking about ASM class?
Yes, I am talking about ASM class, sir.
Yeah, so ASM class is on Monday at 3:05.
That is changed.
Afternoon. Yeah. In fact, it was. I thought it was discussed in one of the lectures. Friday morning lecture, we discussed this actually.
Okay, sir. I missed that class, sir. I think that's why I didn't understand what you are.
I see.
I think Monday 3 to 5
and this one.
This one 3 to 5.
Yeah. So in fact, I had told Kaustubh that I'll send a mail, and I forgot actually. I think
no problem, sir. No problem. But there is no class for Friday.
There is no class on Friday. Yes.
I wrote the timings on the chat. You can say it.
Please, anybody, please WhatsApp me. Then I can understand.
Yeah.
Please.
I'll WhatsApp you the entire timetable.
Okay. Because I want to take this course for credit, so that it is very important for me.
Okay. Anyway, my notes are there on the in the Dropbox. Okay. I hope you are kind of able to access that.
Okay, sir. If I have any doubts, I will mail you, sir.
Yeah, sure.
But you are so tight, sir, because you are teaching 3 courses. I know.
It's okay. No, that's fine. No problem.
Okay, sir. Thank you, sir.
Okay. Yeah. So coming back to what we were saying about this table, the last column, as I said, was computer simulation. The one before that, 2D Ising model, is an exactly solvable model. In fact, it is. You can get the exact partition function at arbitrary temperature. That is the Onsager solution. And of course, these critical exponents you would get only in the neighborhood of the critical point where the Ising model makes transition from paramagnetic phase to ferromagnetic phase. And as you can clearly see that these numbers don't agree with the experiments, which are of course done on intrinsic 3-dimensional system. And that's why they agree with the 3D Ising model reasonably well, but not with the 2D Ising model. Mean field theory does not really agree with either 2D or 3D Ising model, and also does not agree with the experiment very well. But nevertheless, it does not give answers which are like way out of kind of expectations, but they are still in the neighborhood. Okay, but this is not to say that like therefore mean field theory is reliable, but at least it puts the theory in perspective as to where it stands with respect to realistic data. Okay, fine. So any questions about this one? As I said, this is essentially a table picked up from the Goldenfeld's book. So all the data written here is basically the data from that book. I think it's a table on page 111 or something. I'm not 100% sure of the number, but I think that is the kind of page. Yes, 111. Okay, so you can look up in case you want to read something about the table and related information. Okay. Now, one important thing that we should kind of remember uh, before we kind of say anything, even if before we kind of dismiss the mean field theory, and that is that the Hamiltonian that we have written down uh, for the system is analytic both in coupling as well as in dynamical variables. By that I mean that the couplings that appear are appearing in the Hamiltonian with positive powers and positive integer powers, as well as dynamical variables appear like that. There is no dynamical variable sitting in the denominator, or it doesn't appear as some square root value or stuff like that. So Hamiltonian is an analytic function of couplings as well as dynamical variable. Okay. Nevertheless, we still see non-analytic behavior in the thermodynamic quantities, like factors like 1/4, 1/2, or some such thing, or in this case you get 7/4 and stuff like that. This non-analytic behavior happens in spite of Hamiltonian being completely analytic, both in couplings as well as in dynamical variables. Okay, and the interesting aspect of this is that in spite of mean field approximation being very crude, even mean field approximation manages to pick up this non-analytic behavior. Okay. Now, in critical phenomena, it is just non-analytic behavior which is important. Actually, that is the one which picks up the universal behavior of the system. Analytic behavior, analytic pieces in any of the thermodynamic quantity are of not so much interest. Okay, they are not very interesting from critical phenomena point of view. It is a non-analytic behavior which is important and which classifies the systems into different universality classes. Okay. Now, clearly this fact that even mean field theory manages to pick up the non-analytic behavior implies that it has nothing to do with specific dynamics of the Hamiltonian, but it has more to do with the fact that we are trying to take thermodynamic limit. In other words, you have finite system. The finite system may behave in certain way, but an infinite system could develop some kind of non-analytic behavior. Okay, so that is a kind of uh, crude explanation that one could give for the fact that we observe non-analytic behavior even within the mean field approximation. Okay, now let us try to look at the free energy density for this system. Okay, and the free energy density is negative definite. Okay, because it's like -1/n times beta times log of q. Okay, so it's a negative definite quantity, and the free energy density as a function of all these variables h, j, t, and all is a continuous function. Okay, so in that sense, it's a well-behaved function. And if you look at the partial derivatives of f with respect to any of these quantities, okay, then those partial derivatives are also well-defined almost everywhere. Okay, so it's not just that the function is continuous, but it is almost differentiable. Is differentiable almost everywhere. Okay. So, for example, if you look at del F by del T piece, then that is related to entropy density, and the entropy density S is minus del F by del T, and this quantity is positive semi-definite almost everywhere. Okay, so that is the kind of behavior this system has. Okay, now we could ask what happens to the second derivative, and del squared F by del T squared is negative definite, okay, or negative semi-definite in fact, which means that the specific heat is, which is the negative of this times the temperature, is positive semi-definite. Similarly, del squared F by del H squared is negative definite. That's why the susceptibility turns out to be positive. Okay. Now, these kind of properties are the properties of what is called a convex function. Okay, so let's try to understand what is a convex function. So a function f is said to be convex up if and only if for all alpha 1 and alpha 2, such that alpha 1 and alpha 2 take values between 0 and 1, and alpha 1 plus alpha 2 is equal to 1. For all such alpha choices of alpha 1 alpha 2, f alpha 1 x plus alpha 2 y is greater than or equal to alpha 1 times fx plus alpha 2 times fy. Okay, this is the definition of a convex subfunction. Okay, so let me just try to plot a convex subfunction just to give you an idea. So this blue line is a function which would qualify as a convex subfunction.
Sir, please show me the previous slide.
Yes.
1 minute, sir.
Yeah.
What are alpha 1, alpha 2, sir? Those are real numbers?
They are real numbers, yeah. They are numbers which take values between 0 and 1.
So thank you.
Okay. So convex subfunction is something like this blue line, okay, and this amber line is actually a straight line, okay. So if you draw a straight line from, or I don't want to use the word straight line really, if you draw a chord between any point on this curve to any other point on the curve, okay, that chord would lie always below that curve, okay. If you have a function like that, that kind of function would be called convex up. Okay. Now I have of course drawn a straight line. That's why it crosses this curve. But if you look at this straight line as a chord from one point on this locus to another point on the locus, then you can see that that chord is always below the function. Okay. So functions of these kind are called convex up functions. Okay. Of course, you can define convex down function, which is exactly opposite of this, where if you draw a chord, it would always be above the function. Okay. Okay. So a function f is said to be convex up if following things are true. First of all, that it should be continuous function. Secondly, it should be differentiable almost everywhere. Okay. So of course, when one says almost everywhere, means there could be a point where it may not be differentiable. Okay, so that is the reason why one is being careful in saying that it is differentiable almost everywhere. Okay, and the second thing is, and the third thing is that del f by del x for this function is a monotonically non-increasing function. Okay, so that is the kind of behavior we have here. The entropy is positive semi-definite. Okay. But that is negative of del f by del t. So del f by del t is negative semi-definite. Okay, that is the property that a convex up function has. Okay, so what we find is that like we actually can define behavior of certain thermodynamic quantities in these kind of models by just studying certain properties of functions which are either convex up or convex down. Okay. So we will kind of get back to this later, but this is a kind of definition which would be useful for us. Okay. Now let us kind of look at the symmetries of this model. So to understand the symmetries of the Ising model, let's kind of write down the Hamiltonian again. So this is the Hamiltonian with minus j si is j minus h si, sum over nearest neighbor interactions and so on. Okay. Now, notice one thing, that this piece, the Hamiltonian contains a piece quadratic in spin as well as linear in spin. And because of this, it has two types of symmetries that we will be talking about. One is a symmetry which is called time reversal symmetry. Time reversal symmetry corresponds to switching the sign of the magnetic field. Okay, so if you switch the sign of the magnetic field, then the Hamiltonian becomes minus j si sj plus h times summation over si. However, if you flip the signs of the spins, okay, then the Hamiltonian is invariant. Okay, because this term is quadratic, which wouldn't flip sign, but this term is linear. So if si flips sign and h flips sign, then the Hamiltonian is invariant under that. Okay, so that is what is called the time reversal symmetry. H is a function of j h and si, and if you take h to minus h and s to minus s, the Hamiltonian is invariant. Okay. And let us Yeah.
So why is magnetic field changing sign?
No, magnetic field is not, I mean, you can change, this is an external stimulus, right? You can change the direction of the magnetic field, right?
Oh, you're just saying that if we change it, then
Yeah. So I'm saying that if I change the external magnetic field direction, okay, but simultaneously relabel my spins to be minus their own values, okay, then the Hamiltonian remains invariant.
but why are we calling this time reversal then?
Oh, because under time reversal, magnetic field flips sign. That's why it is called time reversal symmetry. Okay.
I think, sir, the equation of motion
Yeah.
of a charged particle in magnetic field
Yeah.
is invariant under time reversal if we change the direction of magnetic field only.
Yeah. Yeah. So that's what I was saying. That under time reversal, the magnetic field would flip sign. Okay. So invariance of under time reversal would require flipping the sign of the magnetic field. Okay.
Okay, sir.
Okay. So that is the reason why flipping H is basically referred to as time reversal symmetry. It goes back to this symmetry appearing in electrodynamics actually. Okay. So let's try to see how it shows up in the partition function. Okay. So partition function is written in this fashion. It's a function of the coupling JH and a function of temperature. And you write that as sum over all configuration every spin would take exponential of minus beta H. Okay. Now, if you make changes in H, if you take H to be minus, I mean, you change the magnetic field direction to the opposite of its original direction and swap spins, okay, then the first line expression becomes the second line expression, which is exponential minus beta H J minus small h minus Si. But remember one thing, when you write down partition function, you're summing over all configurations. Okay. So if you're summing over all configuration, then summing over minus Si is same as summing over Si. Okay. And therefore you could happily skip this sign when you're looking at the partition function. And therefore you can write down this quantity as exponential of minus beta times h of, which is a function of j minus small h and all si's. Okay. But that corresponds to the partition function with only h flipping its sign. Okay. In other words, partition function should be an even function of h. Okay. That's what we get by just looking at the time reversal symmetry of this Hamiltonian. Okay. Now, remember the free energy density is related to log of this Q. Okay. So if you do this transformation, which tells you that QJHT is QJ minus HT, then the free energy is related in this fashion, that FJHT is equal to Fj minus HT. Okay. So like the partition function, it is an even function of the magnetic field. Fine. Okay. So next thing that we would look at is what is called a sublattice symmetry. Okay. Now, sublattice symmetry is a symmetry which is applicable only to bipartite lattice. When I say bipartite lattice, I mean that a lattice which can be divided into two sublattices. Okay. So just to give one example, if you are looking at, say, binary alloy system, then if you recall, I was telling you that, like, there are two different ways of looking at a binary alloy. You can think of copper atoms occupying the vertices of the cube and zinc occupying the center of the cube, which is called the body center position. And conversely, you could think of zinc occupying the vertices of the cube and copper being at the body center. Okay. So given this configuration, you can kind of divide the lattice into a lattice occupied by copper atoms and a lattice occupied by zinc atoms. Okay. Now this is just for the nomenclature purpose. In realistic system or in a system where one is looking for phase transitions, more interesting configuration of copper and zinc atoms would occur. But just to be able to distinguish different lattices, I am just calling one lattice as copper lattice and the other lattice as zinc lattice. Okay. A lattice of this kind is called a bipartite lattice, where you can actually call one sublattice as sublattice A and another sublattice as sublattice B. Okay. Now, if you do that, now remember, look at the look at a simple cube. Okay. If you are looking at a simple cube and at every vertex you put say copper atom, and if you keep a zinc atom at the center of the cube, then the distance of an atom at the center of the cube with vertices is smaller than the distance of atoms which are from one vertex of the cube to another vertex of the cube, right? Okay. Imagine, like, cube, every side of the cube has length 1. Okay. Then the center to any vertex, that distance is smaller because it is square root 3 by 2 is smaller than 1. Okay. Is that okay? So therefore, yeah. So therefore, what happens is that, like, in such form of the lattice, nearest neighbor interaction is going to be between copper and zinc. Okay, and not between two copper atoms or two zinc atoms. Okay, so the reason for giving this example is that, like, if you can divide lattice in this form, this can happen only if the lattice is bipartite, exactly the way I explained. Okay, if you can divide the lattice in that form, then this interaction that we have written down. Okay, yeah, maybe I don't go down, but just split the screen. Yeah, sorry, it took some more time than I thought. Okay, so so if you can divide the lattice into a bipartite form, okay, then the sublattice A would have a nearest neighbor sitting on sublattice B. Okay, so here, when you have Hamiltonian with nearest neighbor interaction, if SI is on sublattice A, then Sj is on sublattice B. Okay, and vice versa, of course. Okay, so if that is the case, then the partition sum that we have written down, which is just the next page here, okay, that can be divided into partition sum over two sublattices. Okay, so we can write that as sublattice sum. So summation Si plus minus 1 can be written as sum over SiA plus minus 1 times the sum over SiB, which is also plus minus 1. Okay, so I'm just writing about this sum. Okay, the function, of course, has to be there. Okay, now if you have a bipartite lattice and where you can do this split, then the Hamiltonian has an interesting symmetry that, so let me write down, go back to the Hamiltonian again. Okay, the symmetry is like this, that the original Hamiltonian can be written as a Hamiltonian written in terms of J, H, SiA, SiB. Okay, that is how you would write down. Okay, now for the time being, let's set H equals 0. Okay, so that we don't have to worry about what the external stimulus would do. But if you flip the sign of J, okay, if you flip the sign of J, then you of course have flipping the sign here. Okay, but you know that Si, if Si belongs to sublattice A, then Sj belongs to sublattice B. So what you, and of course you're summing over all these configurations. So what you could do is that you flip the sign of J, okay, and you can soak that up by just flipping the sign of one of the sets of spins, okay, either on sublattice A or on sublattice B. Okay, so so you go back to original J value, but swap Si to minus Si or Sj to minus Sj. Sorry, SIA to minus SIA or SIB to minus SIB. Okay, one of the two. Okay, fine. Okay, so that is the kind of transformation. Okay, now let's try to see how this reflects into the partition sum. Okay, so let's look at the partition function, and the partition function would be written as usual, sum over all the spin configurations, and we want to look at Q minus J0T. Okay, no external magnetic field, and this is the setup. So that is the sum over all spins exponential minus beta with minus J0 SI. We divide this SI into SIA and SIB and write down this expression. Now, of course, we are going to sum over both sublattice spins. Okay. Now, the Hamiltonian symmetry of the Hamiltonian tells us that we can kind of write down this quantity by swapping the sign of the spin. Sorry, I should have written this at J. Okay. Okay, it doesn't matter. Okay. So I could have kind of traded off the signs of J to sign of SIA. Okay, that is what this Hamiltonian tells us, right? So I should have written really J minus spins here, and the B lattice spins are untouched. Okay, but the point is that, like, you know, since we are summing over all spin configurations, sum over minus SIA is same as sum over SIA. Okay, so therefore this expression is same as this expression. Okay, because we are summing over all possible values of SIA. Is that okay? So as a result, you get the partition function defined with respect to original value of J with SI and A and SIB. Okay, so that is our original partition function. Okay. So what we find is that the partition function written for positive J is same as the partition function written for negative J. Okay, now that is a bit odd. Why is it odd?
Because it can the behavior is changing. Like initially, two particles would two spins would like to align together in the same direction, and now they are wanting to align in opposite direction.
Exactly. So in fact, J clipping sign would tell us that the system should actually behave like an antiferromagnet instead of being a ferromagnet, because ferromagnet would have neighboring spin wanting to point in the same direction, whereas antiferromagnet would want neighboring spins to point in the opposite direction. Locally the energy is lowered by spins preferring to be in the opposite direction. Okay. Now,
but still, it does not have like such a like drastic like change, because like like the two sublattices have same spins.
two sublattices are the same spin, but they are there is a sublattice ferromagnetism. That's what you want to say?
Yeah.
Yes, of course. In the antiferromagnetic system, one defines what is called a staggered magnetization, as against the magnetization that one defines in the ferromagnetic system. Okay, where staggered magnetization is defined as magnetization of one sublattice minus the magnetization of the other sublattice. Okay, and since the sublattices have oppositely oriented thing, this staggered magnetization is a non-zero value, but that happens in antiferromagnets. But the nearest neighbors are of belong to different sublattices, and therefore locally the energy is lowered by spins actually pointing in opposite direction in the case of antiferromagnets. Okay.
So will this in any way contradict the result that we got from mean field theory?
No. What we are going to conclude from here is that the thermodynamic limit, thermodynamic behavior of the ferromagnet and antiferromagnet is same. Okay, within the easing class, this is what would happen.
Okay.
So last time what we saw was that f was an even function of h. Okay, now what we find is that f is an even function of j also. Okay, so as I said that j greater than 0 is ferromagnetic, j less than 0 is antiferromagnetic. So what we conclude basically is that whenever you have a bipartite lattice, the ferromagnetic and antiferromagnetic Ising model have same thermodynamics. Now, bipartite lattices are not very abundant, by the way. In fact, most of the interesting systems are not bipartite lattices, and most of the interesting antiferromagnetic phenomena happen because the lattices are not bipartite. Like for example, if you imagine a lattice which is triangular, okay, let's look at just planar system and take a triangular lattice. Okay, that means it's an equilateral triangle. If you kind of construct the full lattice, it would look like a hexagonal configuration in some sense, but the basic unit is a triangular unit in that case. Okay, if you look at a triangular unit and if you have an antiferromagnetic interaction, then you get a interesting configuration. Suppose in that triangle, two of the lattice sides are arranged to have spin up and spin down. Then the third lattice site would have trouble deciding which way to point. Okay, because if it points in the up direction, then it is antiferromagnetic with respect to one of the spins, but ferromagnetic with respect to the other. Okay, if it points in down, it is in the same state again. It is ferromagnetic with respect to one and antiferromagnetic with respect to other. So if you have a triangular lattice with antiferromagnetic interactions, nearest neighbor interactions, then you have a configuration where three spins cannot form a stable configuration. Okay, fine, because if two spins choose to be one up and one down, then the third spin has no stable configuration available. Such kind of configurations are such kind of systems are called frustrated systems. Okay, and if the system is frustrated, then it generates some specific kind of dynamics, which kind of is which is supposed to be interesting, useful for studying many realistic systems. Okay, so in fact, frustrated antiferromagnets are much more studied than say antiferromagnets and bipartite lattice. Although I must say that initial study of antiferromagnets were on bipartite lattice because the models were much simpler to study. Okay, so yeah, so antiferromagnetic interactions are of interest for various different reasons, besides of course them being part of the high density superconducting systems. Okay.
Sir,
Yes.
sir, here you showed that that when we make j minus j, it is kind of an even function, and but
Yeah.
for that h has to be 0. But
Yes.
if I change j to minus j and h to minus h simultaneously,
Yeah.
then this will not. Then there will be a problem because I cannot make SIA minus SIA like that.
Yeah, that is true because when you do this sublattice configuration, okay. Yeah, so let's go back this thing. So maybe I have it here itself. Yeah. So the point is that like when you write down a partition function, maybe I go to the partition function configuration. Okay. So when you write down a partition function, you are summing over all configurations, right? Is that okay? You are summing over all spins.
Yes, yes.
So even if your h was not equal to 0, you could have still kind of made a statement about what happens to the system. Okay. Is that fine? Only problem is that half the spins would have been aligned opposite to the magnetic field. Okay. And that is kind of that is the kind of thing that would have given us trouble in deciding how f is a function of j, because f is a function of j can be determined from this bipartite lattice in this particular fashion. But if you have a magnetic field turned on, then when you swap SI A to minus SI, okay, then the sublattice spins would be pointing opposite to the magnetic field. So that is more like a diamagnetic behavior, okay, which is something you wouldn't have expected in a system like this. Okay, that is the reason why one is setting magnetic field to 0. So you wouldn't see this symmetry, uh, the yeah, what did I call that? The symmetry, the sublattice symmetry. If you turn the magnetic field on,
Sublattice.
yeah, if you turn the magnetic field on, you wouldn't see this symmetry. Okay.
Okay.
Yeah. Fine. Okay. So, so what we have seen so far is that we have done the mean field approximation to study Ising model, and we studied this in arbitrary dimension. We did not really mention in how many dimensions we are studying the Ising model, but we find that in d dimensions, in mean field approximations, the Ising model undergoes paramagnetic to ferromagnetic phase transition as we lower the temperature. Okay. Now, as I have emphasized several times, that this is a very crude approximation, but still manages to show that there is a transition, and of course it has been observed experimentally. So in that sense, one can say that mean field theory at least manages to crudely reproduce the structure that one sees uh, in the realistic systems. Okay, but we could still ask a question that, imagine that you don't know anything about experimental data, and mean field theory told you that this phase transition happens. Okay, and you know that mean field theory is kind of very, like, crude approximation. You should be doing much better than that. Okay, you could ask a question that, are we really sure that this transition happens? Okay, that, or only mean field theory sees it, and if I do more accurate calculation, nothing of this sort really happens. Okay, now what I plan to do is to give you arguments in support of both sides. In other words, I'll first argue that there is actually a phase transition. Okay, and then I'll argue that actually there cannot be any phase transition. Okay, so we will see both the arguments, and then we'll try to argue as to why uh, the phase transition actually happens. Okay, so today's class most likely is going to be short because I'll give you only one part of the argument, namely argument in support of the phase transition. Okay, so here's the argument. So the free energy of the system is defined in this fashion. It is internal energy minus T times S. Okay, and S, which is the entropy, is essentially a measure of the number of states accessible to the system at a given temperature. Okay, so you are looking at the system, it has kind of all kinds of possible configurations, but at a given temperature, only certain configurations are actually accessible. Okay, and the entropy is a measure of that. Okay, so as you provide more energy, more thermal energy, or as you increase the temperature of the system, uh, more and more states will be accessible for the system to get into, and if that happens, then the entropy will increase. Okay, and so therefore, as you go to higher and higher temperatures, you will find that the entropy will play a more dominant role in this equation. Okay, so high temperature behavior of the free energy of the system is in some sense dominated by the entropy. Okay, so it's essentially an entropy game there. Okay, on the other hand, if you are at low temperatures, then at low temperatures, because very low thermal energy is available, the system cannot jump around between various macro states that are in principle uh, seem to exist. Okay, the system may not have sufficient energy to jump from one macro state to another macro state, simply because it would cost much more energy than the average thermal energy available. Okay, and if that is the case, then the entropy of the system is lower, Okay, and as a result, it is the internal energy which will dominate the behavior of the free energy. Okay, so if that is the case, then you see that there is a transition between which thermodynamic variable dominates the free energy. Okay, at high energy, sorry, at high temperatures, it is the entropy which is ruling the roost. Okay, on the other hand, if you are at low temperatures, it is the internal energy of the system which seems to play important role. Okay,
So shouldn't U also be small when temperature is small?
U, no, U is the internal energy of the system, right? So it's kind of defined per degree of freedom, essentially, right? So
Uh, yeah, but when we are saying the number of accessible states is small, we are defining in like we define entropy in energy space, right? We say that in like in this E2 delta E, E plus delta E,
yeah,
how many accessible states are there?
that's right.
So we define entropy in terms of energy itself.
Yes, exactly. But in but that is but the internal energy is even if it is lower, okay, it is a question of what is the differential between the energy, which is where the entropy gets in, whereas what is the absolute value of the energy, right?
Yeah.
So what I'm trying to say is that the absolute value of the energy continues to be larger. Uh, it's just that if the entropy overpowers, then the T times S factor would dominate. Okay, but
I
that's,
mean, you could take the case of ideal gas,
yeah,
where the total energy itself is small at low temperatures. Like it is,
yeah,
like it goes as 3/2 kT somewhere.
that is right. So when I say low temperature, I don't mean like we are going to uh, like uh, I mean much below room temperature or something. Remember, like the transition that one is looking at is of the order of 1000 Kelvin. Okay, so the energy available is not small actually. Okay, but the entropy of the system would be overpowered by the energy that is available to the system. Okay, so that's what I meant. Okay,
Okay, yeah, I
now
got it.
if you go to very low temperatures like few degree kelvins or millikelvin or something, then yes, then you also would be suppressed quite a lot. But our systems are at reasonably high temperatures, really. Okay, but what I'm trying to say is that like if you go beyond that, if you go to say, know, uh, 10 to the 6 degree Kelvin, then it is completely entropy game. You know, the internal energy is not as important as entropy. That is why the system has much more disorder at that temperature than it would have at say 500 degree Kelvin. Okay, that is the kind of argument that one is trying to give. Does it make
Yeah.
sense?
Okay. Yeah.
Okay. So yeah. Okay. So the point is that like if the microstates of the system are different, if you are in the entropy dominant domain versus if you are in the internal energy dominant domain, then we would say that the system has actually undergone a phase transition. Okay. Now, in our Ising model, of course, in the entropy dominated domain, we have microstates which describe paramagnetic state. Okay. Whereas in the internal energy dominant domain, we have microstates which describe the ferromagnetic structure of the system. Okay. So if one finds characteristically different uh, behavior of the microstates, then we would say that the system has actually undergone a phase transition. Okay. So besides saying that like whether entropy is dominant or internal energy is dominant, we also need to kind of check whether the microstates are in fact reflecting this behavior or not. Okay. But of course, you do see F swapping the sign as one term dominates over the other. Okay. Okay. Now, if you recall that when you study statistical systems and when you try to write down partition function, then of course you may know the spectrum of the system, But when you take the thermodynamic limit of that system to write down the partition function, then what really matters? Hello, can you hear me?
Yes,
Yeah.
we can.
Yeah, sir.
Okay, because it showed that my internet connection is unstable, so I was a little worried because HRI internet is still not on. Okay, let me just keep my phone at the appropriate place so that hopefully I'll get better network. Okay, coming back to what I was saying, that so when you go to thermodynamic limit, then what you do is that, like, whatever quantity that you write down when you write down this partition function, then partition function is sum over all possible energies that a system can have. Okay, now of those energies, the ground state energy would give you the most dominant contribution to the partition function. Okay, because that is the e to the minus beta times E naught, and all other energies are higher, and therefore e to the minus beta E naught plus delta E naught, or you know, any other value which is accessible to the system, okay, which is larger than E naught, that quantity is smaller compared to e to the minus beta E naught. Okay, so in the thermodynamic limit, you say that the dominant or the main contribution to the partition function comes from the ground state, okay, ground state energy, and all other contributions are exponentially suppressed. Why? Because if you pull a e to the minus beta E naught out, then the next term, so then the expansion would be written as 1 plus e to the minus beta E naught plus delta E upon E naught. Okay, or rather E naught plus delta E minus E naught, excuse me. Okay, so that piece is still exponentially subleading compared to the leading piece that one has pulled out. Okay, so therefore in the thermodynamic limit, writing down partition function is really a game of figuring out what is the ground state energy of the system. Okay, fine. Of course, that would require the system to be at finite temperature. If the system is at, say, infinite temperature, that means beta is equal to 0, then of course the structure is totally different. But we are not really looking at systems at very at infinite temperatures anyway. Okay, fine. So the point, therefore, is that the macroscopic, the large scale state of the system is therefore determined by how the ground state of the system really behaves. Okay, and as you start changing the parameters of the model, like, you know, the parameters of the model, of course, are the parameters on which the partition function depends. That is like J, H, and T in this particular case. You would want to ask, how does the ground behavior of the ground state of the system change? And if it does, then of course it will change the large scale or macroscopic behavior of the system. Okay, macroscopic state of the system. Okay, fine. So one could ask a question: what happens when temperature T is equal to 0? Okay, so yeah, so if T is equal to 0, then you get beta going to infinity, and in that case, ground state would dominate maximally. Okay, so that is the configuration that you would have at 0 temperature. Okay, now suppose we denote a system. Oh, I think I don't have a complete argument typed yet. Okay, so yeah, I'm sorry. I thought I had a full argument typed in, but I don't have it. Okay, so in any case, I can kind of still complete the argument. Okay, so the argument is basically like this: that if you set a temperature T to 0, and that means beta goes to infinity, in that case, like, you know, when beta goes to infinity, none of this really makes sense. Okay, because you have like e to the minus infinity, which is like everything looks like 0. Okay, we want to ask a question that in that limit, what happens to the system, and how do we kind of describe the ground state of the system? Okay, Now suppose we have a bunch of couplings. Let's call that entire set to be K. Okay. Then if there is a transition at zero temperature itself, okay, then we want to ask a question that what happens to the system as you change the set of couplings. So you have various couplings like, you know, K1, K2, K3, dot, dot, dot. Okay. As you start kind of modifying those couplings, holding the temperature fixed, okay, what happens to the system? Okay. Now, clearly in this case, the availability of various possible microstates is not of any importance at all, because that number is not playing any role, because there is no energy available to transit between one state to another state. Okay. But what can happen is the following, that you may have a particular spectrum of the theory, and as you start changing the parameters of the theory, okay, so I'm just drawing some picture, okay, as you start changing the parameters of the theory, your spectrum changes, okay, so you have some value which kind of changes in some fashion, some other eigenvalue changes this way. If you start looking at the lower and lower eigenvalue, you have, as you change parameters, you have your ground state which kind of changes slowly with respect to that as you start changing the parameter, and maybe a first excited state also changes. Okay. And it may so happen that if you do a finite change in the parameter, then at some point there's a level crossing. Okay. Now remember, it is this state which has been kind of determining what is the structure of the thermodynamic system that we are looking at. Okay. Right. So in fact, at zero temperature, we really do not even need to take thermodynamic limits, simply because the entire game is dominated by what is the behavior of the ground state, and it doesn't matter how many spins or how many dynamical degrees of freedom kind of are being used in the system to define a ground state. Okay, because you are really only concentrating on the ground state. So as you start changing one particular parameter is what I'm showing, but you may have to change multiple parameters. It doesn't matter really. As you start changing the parameter, the ground state continues to be ground state for quite some time. Okay, but at some point there's a level crossing, and from that point onwards, it is this red line which is a ground state, because that is the one which has lower energy. Okay, so a level crossing in the spectrum at zero temperature is an indicator of phase transition. Okay. Okay. So this is the kind of behavior that you would find at zero temperature. Okay. Now the question is, what happens when you are at finite temperature? Okay. Now, if you are at finite temperature, then the result depends on the dimensions of space-time. Okay, whether you are studying a system in one dimension or whether you are studying a system in two dimensions or higher, the result would depend on that. Okay, so what we actually find, which is what I'll argue in the next lecture. I'm sorry I couldn't type the entire lecture today. I somehow thought I had, because I don't know why I thought that way, but anyway. So what we will show is that if you look at a one-dimensional system at finite temperature, okay, so this is a behavior that I'm talking about at zero temperature, that if you have a ground state which undergoes a level crossing, you will interpret that as a system undergoing phase transition at zero temperature. Okay, and this is just completely a parametric phenomena. You change the couplings or various other parameters holding temperature fixed to be zero, and if a ground state makes a transition, you would interpret that as a phase transition in the system. Okay. Now, clearly, if you ask a question from physics point of view as to what is it that is responsible for this phase transition, given that the thermal effects are completely suppressed in this system because you are at temperature T equals zero, this transition can occur in the system only because of the quantum fluctuations. Of course, if you are studying quantum system. Okay, so these kind of phase transitions are called quantum phase transitions, and This is something which is one of the kind of research topics, one of the interesting topics in recent times. In fact, there is a book by Subir Sachdev on quantum phase transitions, which discusses transitions of this type and how the behavior of this kind of transitions broaden in the parametric space as you actually turn on the temperature. Okay. Now, of course, in realistic systems, you do not really take T equals 0 because there is no way of reaching by laws of thermodynamics. You know, you can never reach the absolute zero temperature. But if the temperature is sufficiently low such that quantum effects dominate over thermal effects, okay, then in those situations, you could and in those situations, if you find a transition of this kind, you could safely call that as a quantum phase transition. Okay. So what I'll show in the next class is that for d equal to for d equals 1, there is no phase transition. Okay. But for d equals 2 onwards, we should see the phase transition in the system. Okay. So I think I'll stop at this point, but I can take questions.
Sir, you're describing this for certain classes or certain class of systems, or is it valid for all types of systems?